The Chernobyl disaster did not begin with an explosion. It began with a decision. A decision that, at the time, made perfect sense. It is late. April 25th, 1986. Moving into the early hours of April 26th, inside Reactor 4 of the Chernobyl Nuclear Power Plant, the night shift has taken control. The atmosphere is procedural, quiet, measured. Nothing appears unusual. The operators are preparing for a safety test, a routine one, at least in principle. The objective is specific: to determine whether the reactor's turbines can generate enough residual power to keep coolant pumps running during a power loss. It is not an emergency. It is a verification. The reactor is being powered down. Controls are adjusted. Parameters are monitored. Each step is recorded. There is structure, there is confidence, and there is precedent. This test has been attempted before. It has failed before, but tonight, it will be completed. There is a sense, unspoken but present, that this is overdue. That the system must prove itself. Time passes. The power level drops lower than intended, lower than safe margins allow. But the process continues. Corrective actions are taken, or believed to be taken. The operators remain focused. Nothing at this moment suggests catastrophe. But something subtle has already shifted, not in the machinery, in the assumptions. The reactor they are operating is not neutral. It is an RBMK design, large, efficient, and unstable under certain conditions. This is not unknown. The reactor has a positive void coefficient. Under low power, as water turns to steam, reactivity can increase. In simple terms, the reactor can become more dangerous as it becomes less stable. This behavior is not intuitive, and it is not fully understood. There have been prior incidents, smaller ones, contained, often attributed to operator error, not to design. Warnings exist, but they are fragmented, technical, scattered across reports and internal discussions. No single moment forces a full reassessment. Instead, there is accumulation, partial knowledge, incomplete understanding. The design is accepted because it works most of the time, because it produces energy, because it meets demand. The operators are not unaware, but they are not fully informed. They understand procedures, they understand controls, but the deeper behavior of the reactor, the edge cases, remains obscured. Risk exists, but it feels distant, abstract, and therefore manageable. At least, that is how it appears. The test has already been delayed. Earlier that day, the reactor was scheduled to power down, but demand for electricity kept it running longer than planned. By the time the test resumes, conditions are no longer ideal. The reactor is operating at an unusually low power level. Stability is reduced. Margins are thinner. And yet, the test proceeds. There is pressure, not dramatic, not overt, but present. The test must be completed. It has failed before. There is expectation, from supervisors, from the system itself, that it will succeed this time. Deviations begin. Control rods are withdrawn beyond recommended limits. Safety systems are adjusted. Some are disabled. Not recklessly, but deliberately. Each decision has a rationale. Each step is justified. There is no single moment where someone chooses risk. Instead, there are small accommodations, small reinterpretations. The rules are not ignored, they are bent, because the situation is believed to be controlled, because the operators trust the system, because stopping now would mean failure. The question is no longer, is this safe? It becomes, can we proceed? And then, how do we proceed? The system does not resist. It allows these decisions. It was designed for human operation, and humans adapt. They adjust. They continue, even when conditions move beyond what was intended. The test begins. Steam flow to the turbines is reduced. Power dynamics shift rapidly. Inside the reactor, instability grows. Reactivity increases. Unexpectedly, rapidly. The operators respond. Control rods are inserted. An emergency shutdown is initiated. But the design contains a flaw. In their initial movement, the control rods increase reactivity before reducing it. A brief surge. At that moment, the system crosses a threshold. Power spikes. Far beyond operational limits. Fuel channels rupture. Water flashes into steam. Pressure builds instantly. Then, a steam explosion. A second explosion follows. The reactor core is exposed. The building is breached. Graphite ignites. There is no containment capable of holding it. The system fails completely. Not gradually, not partially, but absolutely. What was controlled becomes uncontrollable. What was theoretical becomes real and irreversible.
Хорошо, отлично, вот так и держать.
Often described as a combination of human error and design flaws. But that description is incomplete. It isolates causes. It simplifies what was, in reality, systemic. This was not a single mistake. It was a system behaving as it had been conditioned to behave. Risk was always present, embedded in the design, distributed through incomplete knowledge, reinforced by institutional expectations. Over time, that risk became normalized, not ignored, but reinterpreted. Warnings did not trigger alarm. They became background. Procedures did not eliminate uncertainty. They managed it until they no longer could. The operators made decisions that, in isolation, felt reasonable. Each step had logic. Each action had precedent, and the system allowed it, because its assumptions were never fully challenged. So the question is not simply, why did it fail? But how did it become acceptable to operate so close to failure? How does a system absorb warnings without changing course? How does familiarity reduce the perception of danger? And at what point does risk stop feeling like risk? At Chernobyl, nothing appeared out of control until it was. And by then, control was no longer possible. And the cost was not theoretical, it was human. Because the most dangerous systems are not the ones that look unstable. They are the ones that feel stable, right up to the moment they collapse. If this analysis changed the way you think about risk, systems, and decision-making, consider subscribing. And if you want to explore the Chernobyl disaster in greater depth, we've included some of the most important books on the subject in the description below. In the next episode, we examine another moment where warning signs were visible, but reinterpreted until action felt unnecessary. Because disasters are rarely sudden, they are usually negotiated. See you in the next episode.